Good morning, ladies and gentlemen. Welcome to this session, which relates to energy storage and conversion. It's my great pleasure to introduce our first speaker, Professor Bruno Scrosati, that will co-chair with me this morning session. I don't exaggerate saying that Professor Scrosati is a world leader in the field of batteries, and I would say even more, material science for energy storage and conversion. He pioneered a lot of work related to rechargeable batteries. I can mention polymeric electrolytes, solid-state electrochemistry for batteries, materials, nanomaterials for batteries, and definitely Professor Scrosati belongs to the, as I say, to the world leadership in the field of batteries in general and lithium batteries in particular. And this morning we'll hear about new generation of lithium batteries. First, Scrosati, please.
Thank you, Professor Arbach, for the nice introduction, and good morning, ladies and gentlemen. It's for me a great pleasure and honor to be here in this important meeting and have the opportunity of presenting you some ideas that we have now on the progress. It's okay? Of lithium batteries. I'm sure that all of you know how a lithium battery works, but just in case of somebody is not totally aware, and to introduce my talk, let me remind you that conventional lithium lithium-ion batteries is formed by a negative electrode or anode, which is graphite, and the positive electrode cathode with lithium metal oxide, most commonly lithium cobalt oxide, and in between there is a medium which is able to allow transport of lithium ions, usually an organic solution. And the cathode is lithium rich and the anode is lithium poor, so the basic process is the shuttle of ions from the cathode to the anode and vice versa. The features of these batteries are mainly a long life and high energy density, and these features made the lithium-ion battery the power source of choice for a wide electronic market. And now you see this is a multi-billion-dollar market for popular devices like cellular phone, M3, laptops, and others. And the market is dominated by Asian countries, before Japan and now also China and Korea. However, it is clear now that the application of lithium battery may span beyond the portable electronics. And in particular, there are some drivers which make lithium battery to be in the front line for application in sustainable transport and also storage of green alternative energy sources. And this is motivated by the growing concern on global warming and the interest in renewable energy. However, there are some limiters which still prevents the full entry of this battery in the market. These are safety issues and raw material price, especially cobalt, and also some requests to increase of energy. So the big question at the moment which triggers the interest in this battery worldwide is whether the present technology can be scaled up for renewable energy plants and sustainable transport, like hybrid vehicles. And as I said before, there are various barriers that still prevent this important step. The main problem is safety, but also cycle life, cost, and performance in wide temperature range are important, and cost, of course. Therefore, now it's also clear that breakthrough in lithium battery technology can only be obtained by moving to innovative chemistries. And this is not confined to one or two of the components, but to my opinion, to all three components. It means electrodes and electrolyte components. So having this in mind, I will try to present you some types of advanced lithium batteries that we have developed in our laboratory. The first example is what I call metal alloy lithium-ion polymer battery. As I mentioned you before, we are trying to renew all the chemistry of the battery. And as anode material, we propose to use, in replacement of graphite, a lithium metal alloy anode. These are materials which have a very great interest because their specific capacity is much higher than graphite. Excuse me. However, the application of this material has been prevented by the large volume expansions that they experience upon charge and discharge, which produce some mechanical stresses, which ended up with a low cycling life. In our case, we have addressed this issue and hopefully solve it by developing a special morphology of the electrode. Here I report the case of tin metal alloy, lithium metal alloy, and we prepare the tin in nano dimensions, however entrapped in a carbon matrix. So actually we ended up with a composite formed by tin into carbon. And the idea here is to maintain a nano dimension. You see on the TM picture on your right that the dimension of the particle is about 10, 20 nanometers. And these particles, as you can see on the left, are evenly distributed within the carbon matrix. Why we did that? Because, of course, going to nano dimension does not prevent the volume expansion, because this is intrinsic of the material. But you see from the left that these particles are separated by large spaces, volume spaces where they can expand and contract without collapsing one against the other. However, it is also important for electrode material not only to have a nanostructure which improves rates and kinetics, but also to have a high tap density, because otherwise we ended up having a very low volumetric energy. And also, if you use nanoparticles as such, their stability is very poor. They react very easily. So in this way, we maintain at the micro level a low dimension particles, a nanostructure, but at macro level we have a dense structure. Of course, the first important thing was to check whether these particular morphologies allow the ongoing of the electrochemical process, which in this case is indicated here. It is full extension. So we we make a cell, a lithium cell, where this material was cycled, And we ran some in situ X-ray, and the red pattern is the one related to the pristine electrode, and the green pattern is the one related after full cycles. So there is a good match. So this indicates that effectively we have a good reversibility of this electrode. This is very important because if we have a full reversibility, then we are expected to have the maximum capacity out from the material, which is about 500 milliampere-hour per gram. Because here we have a tin carbon one-to-one composition. And this is higher than graphite, which is 370. And indeed, as you see from this graph, which reports the cycling test of the same cell, you see that the 500 milliampere-hour per gram are effectively delivered, and they are delivered for a long time, for many cycles, and with a good, very good efficiency between charge and discharge. And this is a very convincing evidence that we have confined the volume stresses and that the material can work for several cycles. However, you see here at the beginning that there are some difference between the capacity used in charge and the one delivered in discharge. And this is a kind of problem that most of electrodes in lithium batteries have. This is called irreversible initial capacity, which is due to a series of effects connected with electrolyte, with electrode, and so forth. But of course, it's not very much welcome for practical application. So we also face this problem, and you see that in the case of electrolytes prepared, we can even have 63% of irreversible capacity, which is a very large amount. But after treating the electrode with a method which is indicated in that publication that now is out, we can reduce the irreversible capacity to as low as 14%, and this is, of course, an interesting achievement. Also, as I was saying at the beginning, it's very important to have chemical stability of the electrode, and here you see on the bottom left some X-ray pattern obtained on a sample left on the laboratory bench for more than 1 month. You see, there is a very good reproducibility of the pattern with no evidence of tin oxide forming. So this is also confirmed that this particular composite structure also provides a good chemical stability and, most important, the handling of the material. As a cathode, we switch from lithium cobalt oxide, which is a little bit expensive and also a little bit toxic, with this nickel substitute manganese spinel. You see the formula there. This is similar to lithium cobalt oxide, is a lithium-ion provider in the sense that it can release and accept back lithium-ion. The main feature of this material is, of course, the low cost, because it's based on manganese, and the very high voltage is working about 4.5 volts versus lithium, as you see in the voltage profile in the bottom left. And this gives some features which are promises of high energy density, and so is attractive for some applications. But, however, there may be issue here because the voltage may be too high to be compatible with conventional liquid electrolytes. So again, we also tackle this part of the battery, and we replace the normal liquid electrolyte with the polymer electrolyte. Actually, more than a polymer electrolyte it's better to call this a gel polymer electrolyte. And this is our materials, our membranes, which are formed by gelifying, by trapping into a polymer matrix, for instance, polyphenylidene fluoride matrix, a typical liquid solution like LiPF6, PCAC. And therefore, this is not a real polymer, but it's an hybrid material, solid and liquid hybrid material. However, as you see from the picture there, the appearance is typical of plastic. And also, we modified the conventional structure of this gel electrolyte by dispersing into the liquid solution some functionalized nano-sized ceramic particles. And this helps, as you will see, in retaining the liquid within the polymer matrix. Also helps in conductivity, and maybe also in stability. You see from that stability curve on the graph that we can extend the application of this polymer up to 5 volts. So this is maybe a possible electrolyte to be compatible with a high voltage cathode that I mentioned before. And here you see some characteristics of this electrolyte. On the right side, you see the conductivity versus time. The conductivity is about in the order of millisiemens, so it's suitable for practical application, and also stays stable for several days. Since the conductivity is mainly given by the liquid electrolyte, the stability of conductivity is usually taken as a good sign of liquid retention within the polymer. You see on the left side typical Arrhenius conductivity, which is tells you that we can work with the material up to 80 degrees, which can be useful for application, maybe EVs. Unfortunately, the conductivity at very low temperature is not that good yet. So what are the advantages of these polymers? They are stable at high conductivity, the high anodic breakdown voltage, and good liquid retention. So these properties, what have I done? Okay. Do we have some difficulties to hear? What is, okay. So we use this electrolyte for making our polymer battery, and you see now the structure of the battery it contains a thin carbon, our composite thin carbon anode, the gel polymer electrolyte, and the high voltage nickel manganese spinel. These are typical profiles at room temperature of this cell, and this is a cathode limited cell, and you see that we obtain 120 milliampere hour per gram, which is very close to the theoretical capacity, and very good and reproducible profiles for a battery which which ranges around 4 volts. So if we take just the value, the electrochemical value, we ended up with an energy density of 400 watt-hour per kilograms. I can tell you that the average energy density of lithium-ion batteries is about 150, 180. However, of course, this is just the theoretical value. And to go to a practical value, we have to take into account the weight of the ancillary components like case, current collector, and so forth. But we are confident that by a clever preparation of the cell, we can obtain about 200 watt-hour per kilogram. Also, since the structure is basically of the nano size, we have good ray capabilities, at 3C, we still obtain a good fraction of the capacity. This is also interesting. And the cycle life of the battery is quite pleasant because you see the very, very low capacity decay of maybe 400 cycles. So the good aspects, I mean the promising aspect of these batteries are in its high energy, high rate capability, and long cycle life. However, as I mentioned you before, one of the major issues that so far prevent the use of lithium batteries for large-scale application is safety. So we know that there have been some accidents with consumer electronics. Some cellular phone has exploded, some notebook went into fire. But as I was telling you before, we now have millions or billions of these products on the market. So even if we have 10 or 20 accidents that are minor and they are not affecting the technology. However, if may happen that the same accidents verifies on a car, then we are really in trouble, and this may stop the application of batteries for this important market. So there are many ways of checking the safety of the battery. Some of them are of the engineer type, like nil penetration, break, short-circuiting, and so forth. We just made a kind of test based on the combination of thermal effects like DSC and TGA, coupled with a mass spectrometer. So in this way, we could see the thermal evolution and also determine the products which were associated with this evolution. And this graph here report the investigation on the cathode side of the cell. So we disassemble the cell and test here the combination cathode and electrolyte to see whether there is some reaction between the cathode and the electrolyte, which is one of the typical side where we can have thermal runaway in a battery. And you see here from the DC curve, see here we have, from the DC curve, we have a minor effect there, about 125 C, and by the mass spectrometer we could identify what happened there. There are some liquid in the polymer electrolyte which is not totally bonded, and so this is related to a minor release of the liquid. And you see that the major heat evolution verifies around 200 degrees. So with this test, we can suppose that this battery is stable up to 200 degrees, and this is maybe a useful indication for checking the safety for determining the safety of the battery. The same test was run now on the anodic side of the cell. Namely, the test was run on a combination between the anode and the electrolyte. We see again the small DSC peak at 120 due to the release of liquid from the electrolyte. And here you see that some effect starts before 200 degrees, so a temperature lower than the cathode side. And this is explainable because in this anode we have carbon, which may catalyze the decomposition. However, again, we can safely operate the battery up to 180 degrees. How much? finish? Okay, I will just run fast now. And the other type of battery that we have is we call metal alloy ionic liquid lithium-ion batteries. And as in terms of anode, is the same that I used before, so I don't have to mention very much here. As a cathode material, we use lithium iron phosphate, which is is a very popular cathode material at the moment because it's cheap and intrinsically safe. And as electrolyte, we use ionic liquids, which is the new class of electrolytes emerging now in the technology. These are mostly room temperature molten salts based on a combination of a large cation and a delocalized anion. Of course, one has to use some lithium salts in these materials in order to form give it the conductivity for the battery. And you see here an example between pyridinium-based TFSI and lithium TFSI. The conductivity of the ionic liquid decreases by the addition of the lithium salt due to the increase of viscosity, but we can still have a reasonably high conductivity here. And from this TGA, you see that this electrolyte is stable up to 300 degrees, 400 degrees. So this is one of the beauty of the ionic liquids, because they can give you a thermal stability and they are not flammable. There are still some problems on the electrochemical stability of ionic liquids, especially in the reduction side. But we have used our pre-treated thin carbon electrode here, and you see that from this picture that this electrode is stable in contact with the ionic liquid. If we did the same with the piece of lithium, the piece of lithium will become black and the ionic liquid yellow in few hours. And in fact, from this impedance spectroscopy, you see the big difference on the expansion of the semi-arc, which is giving you the idea of interfacial reaction, between the thin carbon, which is the black semicircle, and lithium, which is the red semicircle. So these are all the favorable evidence of aspect of ionic liquids. There still seems some concern on their cost, but maybe if we go to large-scale production, it's not going to be a concern anymore. So now this is the battery. Thin carbon anode, the ionic liquid, and the lithium iron phosphate. You see here some typical charge and discharge profile. And the capacity is good, especially at low rate. We still have some problem with rate capability here. These are mostly due to optimization of the ionic liquid and electrode interface. So, of course, there is always a need for more energy, even more energy. So let me just briefly tell you what are the lines for the future. One, of course, is one is the lithium-air battery, which can give you a very high capacity. It can go beyond the capacity of any lithium-ion battery at the moment. And there have been 2 papers which has triggered this interest. And now there are many research and development projects on this battery. The other system is the lithium-sulfur battery. Also in this case, we can imagine an energy density of 3,000 watt-hour per kilogram. This is an enormous amount. This is theoretical one, but even if you go down to 1,500 watt-hour per kilogram, that would be a big achievement. There are, however, some problems here to make this battery feasible, and there is also a big interest in the world to obtain these results, and we are also involved in this. So in conclusion, I may say that We have common types of lithium battery, which are based on the conventional chemistry, and they are used for electronic device. In the next generation lithium batteries, I think there will be mostly solid-state batteries using solvent-free electrolyte, or hopefully our idea of having lithium metal anodes, lithium-air batteries, and lithium-sulfur batteries. I thank you very much for your attention, and if you are interested in ionic liquids, please come to Rome in June. Thank you very much.
Thank you very much, Bruno, for this nice talk. There's no question, there's a lot of fun with lithium batteries. Any questions? Well, I have a question. Bruno, why didn't you use this ionic liquid with the first system? You have this 5-volt system with the lithium nickel manganese oxide spinel. This ionic liquid that you used has a wide electrochemical window. So this could be used also for the high voltage cathode, isn't it?
Yes, of course we could have used the lithium nickel manganese spinel, but we were trying to also to check the behavior of lithium iron phosphate on ionic liquids, because you may know that there is a lot of discussion and controversy on this material. This was mainly the reason. But of course we can use also a high voltage spinel, for sure.
Okay, Bruno, thank you very much. So we have to move on. I want to